Hello! This will be a demonstration of Proposition 9 from Book 4 of Euclid's Elements, which requires us to, about a given square, circumscribe a circle. What we are then given is, naturally, a square. We're going to call this square A, B, C, D. That. A, B, C, D. So, this will be our given square. And the task at hand for us is to circumscribe a circle about this square. Now let's remember what it means to circumscribe a circle about a figure. What that means is that the circumference of the circle lies on all the vertices of the figure you're working with. So in this case, we're going to need a circle that lies on all the points A, B, C, and D. And that's what we have to draw now. We begin by joining the straight lines AC and BD, like so. We do this obviously by postulate 1. And we're going to let them meet at point E. So wherever they do meet, we're going to call that point E. Now, we know that this line here, DA, must be equal to this line AB. We know they must be equal because they're both sides of a square. They're both sides of the same square. So by definition 122, which is the definition of a square, we know that all the sides have to be equal. And so in this case, DA is equal to AB. Now we also know that DC is equal to CB for the same reason. They are both sides of the same square, so they're going to be equal. The DA is equal to AB, and CD is equal to CB. Of course, all four of the sides are equal to each other, but for right now, we're just going to deal with DA being equal to AB, and DC being equal to BC. Now, if we look at these two triangles here, ABC and ADC, we see that they have a common side, AC, like that. So in this between these two triangles, we have two sides equal to two sides, like that. Which means that we can use proposition 1-8, which is the side-side-side congruency theorem. If two triangles have three sides equal to three sides, they're going to be equal in all respects. And the most important respect here, what we're going to deal with, is that DAC right here is going to be equal to BAC right here. Right? So these two angles here, they're corresponding angles of congruent triangles, so they're going to be equal to each other. The angle DAC is equal to the angle BAC. Now we can prove in a similar manner that AC also bisects this angle down here, BCD, like that. We can prove that in a similar way. In fact, we can actually just directly go off of our previous step because the angles here, BCA and DCA, are in the triangles ABC and ADC, so we don't actually have to work with any new triangles. But for the other straight line, or for the other angles that is, ABC and ADC, we can show that they are bisected by the straight line BD in a similar way by showing that this triangle BAD is congruent to this triangle BCD by proposition 1-8. That's pretty easy. I'm not going to go through that. So we have that AC bisects both the angles BAD and BCD, and the straight line BD bisects both the angles ABC and ADC. Now, let's consider the larger angles here. We're going to consider DAB and, what's the other one? ABC. DAB and ABC, like that. Now, these are both angles of a square, and again, by definition 122, we know that all the angles of a square are going to be right angles. And we can say by postulate 4 that all right angles being equal, their halves must also be equal. It's just a simple property of magnitudes. If things be equal, then their halves are also equal, which means that the halves of the angles DAB and ABC are going to be equal, and we actually do have these halves. The angle EAB is half of the angle DAB, so it is going to be equal to the angle EBA because it is half of the angle ABC. So these two angles right here are going to be equal to one another because they're both halves of equal angles, which means then that by proposition 1-6, that if in a triangle you have two angles that are equal to each other, the sides which subtend those equal angles will also be equal, which means that the sides which subtend these angles, EAB and EBA in the larger triangle ABE are going to be equal to each other. And so we can say that the straight line EAB, which subtends the angle EBA, is equal to the straight line BE, which subtends the equal angle BAE. Now, again, we can prove in a similar manner that EC is equal to ED, and all four of these straight lines are going to be equal to each other. We can prove this rather easily, which means that if we have a circle, if we describe a circle with the center here E, and any one of these four straight lines, it's going to pass through the remaining points. So let's say we describe a circle with the center E and the distance EA. Well, then the points B, C, and D are also going to be on that circle. This is sort of extension of proposition 3.9. So Euclid uses it. So I'm also going to use it that way. So again, if we describe a circle with the center E and the distance EA, because EA is equal to EB, EC, and ED, the circle with center E and distance EA will pass through the points B, C, and D. Now finally, we're going to actually make such a circle. With the center E and the distance EA, we're going to make the circle ABCD, like so. And we know that the circle ABCD can exist, we just proved that. And we can do that by postulate 3, obviously, with any point and any distance. From that point, we can describe a whole circle. So we just use postulate 3 there. Now we see that this circle fits the definition of what it means for a circle to be circumscribed about a figure, because all four of the points A, B, C, and D, which are the vertices of the given square ABCD, are also on the circumference of the circle ABCD, which means that this circle ABCD has been circumscribed about the given square ABCD, which is what we set out to do, which means then we are done with the proposition QEF. Just a little bit of a logistical note. I don't have anything to say about this proposition. You may notice that I have a larger board to work with, not because the board is actually larger than the one I was working on for books 2, 3, and like half of 4, but just because I push the chair farther back so I can fit more on the board, so I can have a larger diagram, so I can have more room to write stuff. So if things just appear a little smaller, that's why. Other than that, I have, of course, nothing to say about this proposition, so I'm simply going to move on to 4.10.